another quick example of another kind of diffusion problem. So let's say I am dealing with the carburization of iron. So I have a piece of iron here, so Fe, and let's say it's, this distance is 100 millimeters. So I have iron, 100 millimeters, and now basically where x equals 0, and I'm going to spray and insert basically, let's say there's a concentration, I'm shooting carbon at a concentration of, basically, let's say it's 0.2, or let's say it's 20%, 20% carbon. I want to see how is the concentration of carbon going to vary as a function of x and t. So let's go ahead and solve this problem. So what's the equation we're going to utilize? Let's use our ODE, which was, again, 2 eta dc d eta dc d eta plus d squared c d eta squared is equal to 0. So that is our ODE that we're going to solve. So now we need our boundary conditions. So what's our boundary condition at eta is equal to 0? Well, it's just that our concentration of carbon is equal to 0.2%. Again, you can kind of change those values. You can do 20%, write it in, but anyways, I want to do it as a fraction of 1. What's the concentration at, what do you think about this distance, 100 millimeters? Quite large, right? I'm going to treat this as semi-infinite. How can I be sure? Well, I can figure out what times, if I gave you the diffusivity, let's say the diffusivity of iron. Actually, let's go ahead and look at our PowerPoint slide. Let's see if we can find the diffusivity of iron, or at least a nice little approximation of it. So that's a little bit difficult to see, but let's say that it is 10 to the minus, let's say it's similar to aluminum. So even at 800 degrees Celsius, let's say it's 10 to the minus 15 centimeters squared per second. So we're talking about something that is probably more likely on the order of, let's just say it's really, really fast. Let's say it's 10 to the minus 15 meters squared per second. So if that's the case, we can figure out, we know our length is equal to 100 times 10 to the minus 3 meters. And once we see that this is equal to 10 square root of, we know d, it's this, 10 to the minus 15 times t, I could solve for the time at which this solution is valid. But I'm going to make a semi-infinite assumption, and then I'm going to figure out that this, at infinity, what's the concentration of carbon? 0. So I can go ahead and do kind of a very, very similar solution. So at infinite, I'm going to say this is 0.2. At infinite is going to be 0. At c is that, this is going to be 0.2. I'm going to solve here, and there's my solution. Now I could plot and plug this in. So I'm going to plug this in right here. I am going to insert x over root dt. So actually, let's go ahead. Let's go all the way back here. I like this square root. Let's plug this in for here, except we had minus 15. So let's go ahead. Oops. Plug this in here. So like this. And let's go ahead and change this to minus 15. And let's plug in here. We said that we were dealing with a material that had, what was it? 100 times 10 to the minus 3. Let's see how it looks like. Ooh, that's a small length scale. So let's look at something a little bit small. Let's do 10 to the minus 6. Let's see if that changes. Now we start to see, again, that carbon diffuse in. So again, I think our semi-infinite solution is a valid one. So actually, let's go ahead and prove that, that thing let's see how long that this solution is going to be valid for. So let's solve. So my length is 100 times 10 to the minus 3. Set that equal to 10 times square root of d, which is 10 to the minus 15 meters squared per second, times time. So I'll solve for time. Oof, there's a long time. So that is a nice kind of valid solution. So this is it. This is all you kind of have to worry about when you're kind of dealing with kind of these diffusion problems. So set the ODE, we're going to solve our ODE, set the boundary conditions, see if we meet this semi-infinite approximation, and solve. That's it. Now, one other little trick that you'll often see is an engineering approximation. So lots of times you're going to kind of superpose these kind of solutions, and you could solve a lot of the problems numerically. But when you're out kind of in the field, we are going to be kind of their steady state solution or steady state diffusion as well, so no time varying in the composition. But you can use this engineering approximation for estimating the diffusion depth. So this is very, very handy, and a lot of times it actually is pretty accurate. So one of the things you probably keep seeing pop up is this ERF-like solution. So if we go back into our notebook and we look at the ERF function, we know that once you reach an ERF or an x value of about 2, you start to see that the ERF function becomes essentially flat, 1, meaning that our concentration is, you basically have 100% concentration in that kind of solution there. So if you're estimating about a diffusion depth, or when is there kind of no time varying, when has my material completely penetrated and filled in that material, you can use kind of this engineering approximation. So we're going to substitute in, and we'll say that at approximately at an eta value of equal to 1, we are going to kind of hit our kind of we're basically flat. There's no more kind of diffusion going on. So we could solve for our diffusion depth here. So we can use this expression eta equal to 1, or x is equal to 2 root dt. So we could solve for what is the diffusion depth based on our diffusivity and our time. So this is a very, very handy approximation. If you're ever asked diffusion depth, how long it will penetrate, in this distance, that's kind of the key idea we're working with here. So engineering approximation, you'll see that quite a bit. So excellent. Now that is about it for diffusion. Actually, here we're going to get into Arrhenius, temperature dependence of diffusion, and anisotropy in a second. So see you all in the next video. Thanks.